All right, so special triangles are triangles that have 45-45 situation. Or the other one that we like to really focus in on and memorize is a 60-30, or we sometimes say 30-60-90 triangle. So last week you looked at a video and you learned a little bit about these reference triangles. And what we did is first we labeled one of the sides 1. And I called that sort of the foundational side. That's kind of how I think about it. It's the very initial side. So on the 45, I'm going to call this 1. Right? We just label it 1 inch, 1 centimeter, 1 unit, whatever the heck it is. And then every single 45, 45, 90 triangle will have the following relationship. Is that the other leg will match because it's an isosceles triangle after all. It's isosceles, so they'll match. And then, as you saw last week, you could do Pythagorean theorem to figure out, 1 squared, to figure out the hypotenuse. And the hypotenuse is radical 2. Now, as you learned last week, that means that the hypotenuse is 1.4 times bigger than these legs because square root of 2 is like 1.4. So every single 45, 45, 90 triangle, the hypotenuse is radical 2 times bigger than the leg. So in the video last week, I said if this were 4, then this would be 4 radical 2. It would just be radical 2 times bigger than the leg. Now, what about a 30-60 triangle? Well, again, we have to label one of the legs with a 1. So what we choose to do is typically label the short leg, the shortest leg with the 1, and that is across, right? We call that opposite from the 30-degree angle. So opposite the 30-degree angle is going to be 1. And then, it's kind of neat, the hypotenuse is twice as big. The hypotenuse is twice as big as the short leg. So if the short leg is 1 inch, the long leg, or the hypotenuse, will be 2 inches, guaranteed, if you truly have a 30-60-90 triangle. And then if you do Pythagorean theorem, so we have 1 squared plus b squared equals 2 squared, and we subtract 1 from both sides, we get b equals radical 3. So the long leg ends up being 1.7 times bigger than the short leg here. Radical 3 is like 1.7. So again, that was all from the video last week. We can go ahead and fill in the trig ratios down below. We can fill in the trig ratios down below because we have all the triangles. So sine of theta. If we have a 45, the sine would be 1 over radical 2. And I'm not going to go this slowly in all of these. I just want to show you what I'm doing here. So sine theta for 45, you go to a 45, opposite over hypotenuse would be 1 over radical 2, which if you rationalize it is 2, radical 2 over 2, radical 2 over 2. And then the cosine is exactly the same on the 45. Now the tangent of a 45 is always 1 to 1. 1 over 1. So the tangent of a 45 is 1. And then all those relationships down below are reciprocals. So the cosecant would be radical 2. Secant would be radical 2, and then cotangent would be 1. All I did was flip over that one right there, the 1 over radical 2. I just flipped it over because of those reciprocal relationships we saw when we were defining these functions. All right, now let's look at the 30-60. We've got the rest of the table to fill in here with the 30-60. So sine of 30, so I'm going to go to 30. Opposite over hypotenuse is a half. 1/2. Which means the reciprocal of that, by the way, would be 2. Cosine would be radical 3 over 2. which means the reciprocal would be 2 over radical 3, which is 2 radical 3 over 3. Tangent of 30. Tangent of 30 is where you're right here, opposite over adjacent. So tangent of 30 will be 1 over radical 3, which is radical 3 over 3 when you rationalize it, which means this down here would be radical 3 when you flip over the reciprocal. So you flip it over to get the cotangent. Now, if you think about it, 60 is just coming from a different angle here. 60 is up here. All right, so what used to be opposite is now adjacent. So what happens is this number right here ends up going right here also. They match, as you saw last week. This ends up being radical 3 over 2. Tangent will simply be flipped over. And then this will be 2 over radical 3, which is 2 radical 3 over 3. And then this would be 2. Again, I got all that from this, our reference. These are called reference triangles. And when I have when I've taught trig before, generally it's like a semester course. There's quite a bit to study in trigonometry. Often students will jot that on their paper immediately. Let's look at a couple examples down below. Now, here's the reference triangle from above. 1, 1, radical 2. We're going to use that to solve this. So if this side is 6, how long is this leg?
6.
6. That was easy. They match. How long is the hypotenuse? Well, if the leg is 1, the hypotenuse is radical 2 times bigger. But I'm just going to leave it like this. I'm going to leave it like 6 radical 2. So let's look at the 30-60 example off to the side. Again, the reference triangle that a lot of students write on their paper is here's 60, here's 30. Across from the 30 is the 1. The hypotenuse is twice as big. The long leg is radical 3. So if I give you the hypotenuse, how big is the short leg? If it's a 2-to-1 ratio. 12. You cut it in half. Very good. So 12 kilometers. Now that you have this foundational or unit side, the side that's 1, now you can go over here to the radical 3 side and simply write 12 radical 3 kilometers. All right, so then down below, here's some other stuff sometimes we have to do in trigonometry, and that is just do some calculations using these values that we either get from the table, but hopefully you can picture them in your head and have them memorized. Cosine of 45 degrees is 1 over radical 2. If you look up in the table, that's what I wrote. I happen to have it memorized, and maybe you do too. You can kind of picture that opposite over the hypotenuse. And then sine is exactly the same, folks. So when you multiply straight across, you get 1 over radical 4, which is 1/2. So the answer is 1/2. That simplifies. It says find the exact value. Now on the right, we've got another example. The tangent of 45. So look up in the table. What is the tangent of 45? 1. It's the ratio of the two legs, which is 1-to-1. You can kind of picture that in your head, hopefully. Plus, the cosine of 30 would be radical 3 over 2. So if you add these together, you need a common denominator. So you could simplify it to be like this. Because 1 over 1 is really, or 1 is really 2 over 2. When you add fractions, the denominator stays the same. All right, so make sure you're paying special attention on this next side because this may be 100% new to you. It's probably most of you, it's new. We're going to learn what a radian is, and we're also going to talk about an angle in standard position. when you have an angle in standard position, the initial side is the positive x-axis. So we're going to draw an angle, and we're going to have the initial side on the x-axis. It always starts on the x-axis, positive x-axis. Now, what does the word terminal mean? Terminal side is the end side. So we could have a terminal side here, terminal, which means we could draw our theta in right here. And you see how the theta has direction? It's counterclockwise. It's the opposite of what the clock does. That's what counterclockwise means. All right, so it always starts on the positive x-axis, and then a positive angle goes this way, and that's what this next thing has. So a positive angle would be like this. This would be a positive theta because it's going counterclockwise or anti-clockwise. An angle that starts here and goes this way, this is considered a negative. So this would be clockwise. This would be negative 60 degrees. We could draw a positive angle like this. It starts here, and then it ends here. This might be 100 degrees, positive 100 degrees. Counterclockwise is positive, and clockwise is a negative angle. All right, so I would like you to take a moment and see. Start with that first one. Can you graph 170 degrees? I'll give you a hint. All the way around is 360. All the way around is 360. All right, so let's check your first one. 170 is just shy of what? Just under 180. And I told you that 180 was right here. So this would be 180. So we got to be just under that, folks. And then, in your notes, please draw this arc and put a theta there equals 170 degrees. Just to remind you that that's the angle that we're representing here. Counterclockwise, 170 degrees. As a reminder, we have quadrant names. This is quadrant 1. This is quadrant 2. This is quadrant 3 and quadrant 4. So sometimes I might ask, where is the terminal side? What quadrant do we end up in? Where does it finish? So let me ask you this. What quadrant does negative 300 degrees finish in? Where does it terminate? Very good. Quadrant 1. So here's 90, negative 180, negative 270. We got to keep going. So it puts us right here. So we would put our angle there, and then you need to draw this and put your theta in there. That's negative 300 degrees. And then 240, what quadrant will 240 land in?
3.
Very good, quadrant 3. Here's 180. We got to keep going. In fact, we go 60 degrees past 180. So that ends up being about right there. So this would be 240 degrees. Okay, so we've been measuring angles in degrees, and that's perfectly great. Degrees are fine, often. It's sort of like measuring in inches, feet, and miles. There's an alternative way to measure angles, just like there's the metric system where you have centimeters, meters, and kilometers. It's just a different way to measure an angle, and it's called a radian. A radian. Now, where on earth do we come up with a radian? What does it mean? If you have an arc length where that arc length is the same as the radius, And there's actually a formula for arc length, okay? But just know that if the distance around the circle, this far, matches the radius, you have just gone 1 radian around the circle. 1 radian around the circle. Well, we're not going all the way around. To go all the way around would be 360 degrees. That is 2 pi radians. Write this down, please. So you're on your skateboard or bike or whatever, and you're like, dude, I just did a 360. Now you can say, dude, I just did a 2 pi, man. Because it's the same. Now, what if you did a 180, man? All right, it is 1 pi radians is 180 degrees. This is the definition of a radian over here on the left side. But honestly, this is what I have memorized, and the way I think about it is I simply remember all the way around is 2 pi. Halfway around the circle is 180 degrees, which is 1 pi radian. If you think about the formula for circumference, it's 2 pi r. 2 pi r is the distance around a circle, 2 pi times the radius, diameter times pi. That's where this comes from, the 2 pi. Now, I gave you the conversion here in the notes, but you can also think about canceling units, as I'm going to show you here in a moment. To convert from degrees to radians, we're going to multiply by pi over 180. So let's just do that first, and then I'll talk about converting the other way. So we're going to multiply by pi over 180. So if we have 60 degrees, write this work down, please. And if we multiply by pi over 180 degrees, do you notice that the degrees cancel? We did a unit earlier this year on unit analysis where we converted units and we canceled the units. This is how I think about it, honestly. I don't just memorize, I just multiply by pi over 180. I think about it for a moment and make sure the units cancel. The units cancel, so you get 60 pi over 180. And then you reduce the fraction. They're both divisible by 60. We're reducing fractions. So we get pi over 3. Pi over 3 radians. Pretty rad, right? Negative 120 degrees, we're going to convert to radians. So you write down a negative 120 degrees. I like to put it over 1 so that I can see my units canceling very clearly. I'm going to multiply by pi over 180 degrees. You see the degrees cancel, leaving us with radians. So this is negative 120 pi over 180. These both divide by 60 again, just so happens, similar to the last one. So we get negative 2 pi over 3. Negative 2 pi over 3. It's pi over 4 radians. And again, that's one that I have memorized because 45, 45, 90 is an important reference triangle. I also happen to have it memorized that 45 degrees is pi over 4 radians. In upper level math, I mentioned it up here, calculus and physics, a lot of that is done in radians. So you have to change your calculator to radian mode and while you're working with those. All right, let's convert back now. What about converting from radians to degrees? What we do is multiply by the reciprocal of what we did last time. So we have pi over 12. This is radians. We're going to multiply by the fact that we have 180 degrees is the same as 1 pi radian. We have the unit radian on the top and bottom, so they cancel. You can just think about it that way, that the units simplify, they cancel. And we get 180 pi over 12. Oh, I'm sorry, the pi's also cancel. So we have a pi on the top and the bottom, and they cancel. So 180 divided by 12. So 15 degrees is the answer. This probably isn't mental math for you. You know, you want to show a little bit of work so that you convert between the two. Why don't you try this next one? Convert 5 pi over 4. You should get 225. 5 times 180 divided by 4 is 225. Let me point out, when I wrote this problem, I was thinking I wanted to show you how 45 degrees was 1 pi over 4. So how many would 5 of them be? Well, you just take 45 and multiply by 5. So let me say that again. 1 pi over 4 was 45. So 5 of them would be 45 times 5, which is 225. So that's another way to reason that out. I knew it was going to be a multiple of 45 because I put the denominator as a 4 there. Now, when the denominator is a 3, I actually know it's going to be a multiple of 60. It's going to be a multiple of 60. So let's convert this real quickly, and then we'll be done for the day. Negative 8 pi over 3 times 180 over pi. So the pi's cancel, the radians cancel. 3 goes into 180 60 times. This ends up being negative 480 degrees. Negative 480 degrees on that conversion. All right, so you learned a little bit about reference triangles. We filled in the chart. And then we also, up top here, we talked about some of the vocabulary in having angles in standard position and such. We even sketched some of them. We also we reminded you about the quadrants. So if I ask you what quadrant something ends in, you should know that. And then at the end, we learned what a radian was and how to convert from and to radians.